Hello everyone. In today's video, we will understand how to estimate reliability and availability of an electronic system with real-world example. So let's begin with the basics. In reliability engineering, reliability is defined as the probability that an item will perform its function in its intended environment for a specified period of time. Now notice that this definition is conveying three key concepts on which reliability is based. Firstly, reliability is a probability. It is not a guarantee that a product will function. Rather, it says that there is a chance that product will not function as expected. Secondly, the intended environment. Reliability is a function of the environment in which the product operates. If the environment is harsh, reliability comes down. If the operating temperature or humidity of a system is higher, the reliability is lower. If the environment is controlled, like in an air-conditioned room, it goes up. And thirdly, reliability is a function of the specified time. Now, let us see why reliability is a function of the operating time. We will understand it with a simple example. Let's say Apple is about to launch a new iPhone and wants to do some quality testing. So it has handed out 100 mobile phones to its employees for use. And they are starting to collect the failure data. Now what they observe is the first mobile phone fails after 10 hours of operation. The second one fails after 25 hours of operation. The third one after 80 hours. The fourth one after 300 hours. And finally, the 100th mobile phone fails after only 3000 hours of operation. Probably there is a design issue. But let us come back to our reliability problem. So, what is the reliability of this mobile phone up to 100 hours? As you can see, it is 0.97 because up to 100 hours, 3 mobile phones had failed. So reliability is the number of items that have survived up to 100 hours, that is 97, upon 100, which is equal to 0.97. Similarly, what is the reliability after 300 hours? If you see the timeline, one more mobile has failed after 80 hours. So the reliability now after 300 hours has come down and it is, as you can see, it is 0.96. So can you see why reliability is a decreasing function of time? Because the products fail with time. Now that we have understood reliability, let's move on to another important concept in reliability engineering, that is availability. What is availability? It is defined as the probability that a system is operational and able to perform its function at a given point in time, or it is also defined as the fraction of time a system is up and running. Availability is equal to the uptime divided by the total time, that is the uptime and the downtime of the system. Uptime is the time during which the system is functioning properly, and downtime is the time the system is unavailable due to failures, repairs, or maintenance. With this basics, now let us look at the problem statement we will discuss in this video. A team of engineers in an organization was given the task to develop a data acquisition system which meets a user reliability requirement of 0.95 for an operating time of 1000 hours, and environmental conditions the system will see will be 25 degrees Celsius ambient and relative humidity of 50%, and it also has an availability requirement of 99% or higher. Can you see that reliability requirement is being asked for a certain operating time and certain ambient conditions? So the design team came up with a solution. The DAC system they developed consists of 7 different types of modules. As you can see here, The DAC system has a CPU module, a communication module, and also different types of I/O cards such as analog input, digital output, or analog output. Now all these electronic modules are powered by a power supply module. Now what about its reliability and availability? This is where the role of the reliability engineer comes in. Let's start with system reliability analysis. For this analysis, what is the information required? Firstly, we need to know the system architecture, whether the system has a single channel or a parallel configuration or any other complex architecture. Then secondly, what are the reliabilities of the modules used in the system? And thirdly, what is the reliability relationship between modules? Is it series connection or parallel connection or series parallel combination, etc. Coming to DAC architecture, it is a series system. That is, all modules are required to function for the system to function. Any module failure will result in system failure. We can see the series configuration or the series connection of the 4 types of modules A, B, C and D, which is shown here. Now let's look at the DAC module reliabilities. For this, the design team shares the module design with the reliability engineer. Now the engineer uses this data and estimates reliability for the given operating time and environment as shown in the table here. Now for these different types of modules, we can see their reliability figures. For example, for CPU module, the reliability is 0.95. For a DO card, the reliability is slightly higher, that is 0.98. Now the reliability is decided by the type and number of components used in the module. For example, relays, which tend to be present in the power supply, have higher failure rates. That is why the reliability of the power supply module is lesser here. Moving on, for system reliability analysis, here we take the reliability block diagram approach. The RBD of the DAC system is shown here. Here we can see all the modules are connected in series. Now for a series system, the system reliability is simply the product of all the individual modules which are present in that system. Here we have 7 types of modules, so all their reliabilities are multiplied together. So taking the individual module reliability, we get an overall system reliability of 0.81. Now we can see that this DAC system is not meeting the user reliability requirement of 0.95. So what should be the approach now? This is a very common situation in real engineering systems. In further slides, we will see how to address this. Now let us look at system availability analysis approach. For this analysis, we need only 2 parameters. That is the mean time between failures of the system, which comes from the failure rate attribute of the system. And secondly, the mean time to repair, which comes from the repair rate of the system. Now I have made a video on what is MTBF, its basic idea, whose link I have given in the bio. You can watch it. Now for a single channel series system, the availability is given by this formula we discussed earlier, which is also equal to MTBF by MTBF plus MTTR. Now assuming MTBF of DAC system is 4750 hours and mean time to repair of 8 hours, which is typically assumed taking 1 shift time, we get availability of 0.998. Now this is meeting the availability requirement of 0.99. So now what is the reliability engineer solution to reliability of DAC system? As we saw, single channel DAC is not meeting the reliability requirement. So what he does is, he proposes to use redundancy. that is 1 out of 2 configuration or the parallel configuration, which is a very common technique employed in reliability engineering to enhance system reliability. As you can see in the parallel configuration, there are now two channels. DAC system A is one channel and DAC system B is another identical channel connected in a parallel manner. Now for this parallel configuration, the reliability expression is shown here, which is equal to 1 minus the probability of failure square. Now to get this failure probability, it is nothing but 1 minus the reliability of the single channel, which we saw earlier was 0.81. So this PF comes out to be 0.19. Substituting it in the reliability expression, now we get a reliability of 0.964. Now this meets the reliability requirement of 0.95 and the designers are happy. But then what happens to availability now? For this 1 out of 2 configuration, the availability formula is shown here. Now this formula comes from the Markov analysis for a parallel system. Once again substituting the previous MTBF and MTTR values, now we get an availability of 0.9999. Improved availability. So summarizing now, we have seen the definitions of reliability and availability. We have also seen how to estimate reliability and availability of a single channel electronic system of DAC, and then also how to estimate them for a dual channel DAC. If you have liked my video, please like and subscribe to my channel, and also let me know if you would like me to discuss any particular concepts in reliability engineering. Thanks for watching.